Okay, so we've looked at Ohm's law. We're now moving on to potential dividers. This is the core of how your humidity sensor circuit works. On page 5 you will need to complete the blanks within this section of text and write in what the two rules for potential dividers are, or explanations of those formulas. So we're looking at a potential divider circuit on Circuit Wizard again. Now I've drawn it with a positive and a negative rail rather than a battery, so that's slightly different to the way that you've got it in your booklet. But the reason I've done that is because I want you to understand that when we're looking at a potential divider, we're looking at the voltage that is going into the circuit, so in this case it's 5 volts, and those 5 volts are going to be completely used up over the resistors so that there are no volts left. Okay, so you are always going to use up those 5 volts going through the two resistors. I've put an ammeter in because if we're thinking about Ohm's law, the current is the voltage divided by the resistance. And in this case, because the resistors are in series, in other words, the current has to go through one and then through the next one. To get the total resistance, you add those two resistor values together. So we've got 2K, 2 kilo ohms of resistance, and 5 volts. So the amps is 5 divided by 2000, and that will give us 2.5 milliamps. Okay, now I've put that in just so that as we're going through, the resistance values changes, you'll see that the current changes, but I'm not going to keep referring to it. I've just put it in there for those of you that are wanting to pay attention to what it is. I've also put 2 voltmeters in. Now a voltmeter measures the voltage across a component, so it's put in parallel with the component. So this voltmeter is measuring the voltage across this resistor, and this voltmeter is measuring the voltage across this resistor. The current is measured going through the components, so the ammeter is put in series so that the current goes through the components and through the ammeter. So we've got two resistors. They both have the same resistance. They're both 1K, which means that they divide the potential equally. So our potential difference, our voltage, is 5 volts. Both of these have the same value, so they literally divide the 5 volts in half and we get 2.5 volts across each resistor. Okay, now I'm going to move down. Look at the next one. Now on this one we've still got 5 volts. We've now got 3K in total, which gives us a different current. We've got 2K on the top resistor, 1K on the bottom resistor, and you'll see our voltages across each resistor have changed. Now if you want to do a little bit of maths, what you'll find is that because this is twice the size of this, the voltage across it is twice the size. But equally, if we add these two together, it comes to 5 volts, because as I said to you earlier, the 5 volts that goes in gets completely used up going across these two resistors so that there is none left at the end. So this voltage and this voltage added together will always equal the voltage going into the circuit. This resistor is twice the size of this, so the voltage across it is twice the size of the voltage across this one. Moving down. We've got, once again, two resistors. This time they're both 2K, so in total we have 4 kilo ohms of resistance. So our current has reduced again. It's now down to 1.25. But because these two are the same value, they've got the same voltage across it. And it's 5 volts going in, so it's 2.5 volts across each one. The first circuit we looked at had 1K and 1K. And some people then think, oh, well, this should be 5 and 5. But it can't be, because it has to add up to the voltage going in. Looking at this circuit, we've now got a 1K resistor at the top, 2K at the bottom. Once again, the 1K is half the size of this. Therefore, the voltage across it is half the size. Now if we really want to look at it, we've got a 1K to an 8K. We've got a tiny current going through now because we've got such a high resistance. This letter here is mu. It means microamps. So this is 555 amps divided by a million. Now working in millivolts up here. And if you want to do the maths, you will find that if you multiply this value here by 8, you will get 4.4. So, what is a potential divider? A potential divider is two components or more in series between the positive and the negative rail, because those components will take part of the voltage across each component, and that voltage is linked to the resistance. So in our case, we're working with resistors. So potential divider is made up of two or more resistors which are connected in series between the positive and the negative rail. The total the total voltage in the circuit is divided across the two resistors, and the voltage across the bottom resistor is used as a voltage signal to trigger other components within the circuit. We use these components because we can then set this voltage signal to a particular value. Now if you think about it, we looked at light dependent resistors before. So we've now got an automatic circuit that the light levels affect the voltage and the current flow within the circuit. Okay, so a potential divider splits the complete potential in the circuit. They're also called voltage dividers sometimes, by the way. The voltage across R1 and the voltage across R2 always add up to the total voltage. So V in equals V1 plus V out. So that is literally the voltage across the two resistors added together is equal to the total voltage in the circuit. And the last bit is to do with ratios. So if you watch these values as I change the light levels on this LDR, then the ratio between the values of the resistors changes, and it is the same as the ratio between the values on the voltmeters. Okay, so your final rule, and the formula V out equals V in times R2 over R1 plus R2, is the fact that the voltage, the ratio between voltage 1 and voltage out is the same as the ratio between R1 and R2.